Case 2 might seem like a very large question, but there's actually a lot of information here that we don't really need to bother with. So let me read through and I'll show you what I mean by that. So the question says, Kate Smith is the owner of Veggie Cuisine, an upscale coffee shop selling the finest veggie sandwiches, soups, and excellent coffee. To date, Kate has been preparing all the sandwiches, soups, and drinks herself based on her instincts and experience. However, the long hours of success of the business have necessitated hiring some staff. Okay, so that's nice, but we don't really need anything from there in order to be able to answer our question. So I'm going to get rid of this whole paragraph here. It then goes on to say, onion soup, one of the soups Kate sells, is an exquisitely rich flavor soup with a French touch. Kate's experience is that the ideal temperature for onion soup is 142 degrees Celsius, hot but not too hot. Okay, so now we are going to make use of, we are going to make use of the 142 degrees Celsius, but in this video I'm going to answer part A. And if you have a look at part A does once again remind us that it's 142 degrees Celsius that we're supposed to be focusing on. So I don't even really need anything from the second paragraph because it's contained in the question down below. In the next paragraph it says, while training one of the new cooks, Kate took a random sample of 31 bowls. Okay, so this is going to be useful. Random sample of 31. So my sample size will be equals to 31 of onion soup and measured the temperature of each bowl using an instant read digital kitchen thermometer. Okay, keep this in mind until we get into deciding our formula or which formula to use a little bit later on. Remember that it's temperature that we're measuring. Now, she measures the temperature for each one of these bowls and it's accurate to the nearest whole degree. The data is in the file veggie.xls, so we definitely need to make use of that data file. I've got that data file here, and so you'll see that we've got a list of our different temperatures of bowls of soup, and this goes down to row number 32, but there are in fact 31 observations because the very first row is taken up by the label onion soup temperature. Now in order to make this a little bit easier to work with, I'm going to insert a column here. Okay, so here's our data. We're going to make use of this data, but let's go back to our question and see if there's any more information. Now I've read through this already, and this next paragraph where it talks about espresso, this next paragraph, this large paragraph, is going to be dealing exclusively with parts C, which deals with espresso, and D, which once again deals with espresso. But we're working on part A right now, so we can safely ignore this last paragraph here. So out of this entire setup, all that I really need is what's contained in this little paragraph here, and we're going to make use of our data file, our sample within that data file, and the fact that we have measured temperatures. We're going to use all of that to answer part A. But to answer part A properly, we're first of all going to need to know what are they asking, and then what is going to be the correct chapter and formula to make use, or to come up with our solution. So let's read through part A and see what it says. At alpha equals 10%, so this is the same as saying that my significance level is equals to 10%. So at a 10% significance level, does the sample data provide evidence to show that the true mean, that's another name for population mean, true mean, that the true mean temperature of the onion soup differs from 142 degrees? So is the true mean not equals to, different than, 142 degrees? That's my question. To answer this question, we're going to have to choose the correct formula from a number of different formulas in a number of different chapters. And the best way to do that is to work through a flowchart that you'll also find in your textbook. The flowchart basically categorizes every type of word problem you could have, or really it's about every type of data that you could have, and it helps you link them up with the appropriate formula. And it does it in a series of really simple questions. For example, the nature of the question, the type of question you're being asked, is what comes first. Your question is either going to ask you to describe one population. This would be chapter 10, 11, or 12. Or it could be that you're going to be asked to compare two populations. And that would be chapter 13. So what is it that we've been asked to do here? Well, in our question, dealing with the onion soup, we've been asked to describe one population. Now, an easy way to make certain of that is to have a look at your data file, and you'll see that we've got our list of 31 different onion soup temperatures here. And you'll notice that it's just one continuous list. I just have one sample. I don't have a group of onion soup temperatures and then another group of chicken soup temperatures. I don't have temperatures listed by males and then another set of temperatures reported by females. I just have one continuous sample. And so one sample is going to mean that I have one population. If I was being asked in a question to compare two populations, I would have to have two samples. So we can rule out that we're going to be comparing two populations, and so we can rule out everything from chapter 13 in order to be able to answer part A of this question. But that still leaves quite a few formulas in 10, 11, and 12, so we have some more questions to answer here. And the next one comes down to the data type. What type of data is it that we're dealing with? And there's two basic types of data that we're going to need to worry about, and that's interval and nominal data. Interval data just means numbers, but very specifically it means numerical measurements or counts. And remember how I said that we are measuring the temperatures, whereas nominal data is categories. Categories would be if our data came in this format. If instead of saying 140, what if it just said hot? And if instead of saying 145, it said that this was just reported as being too hot, and so on. Maybe 137 would be called cold. These would be categories, but we don't have categories. We have proper numerical measurements. So we can rule out that we're dealing with nominal data. And so by ruling out that we're dealing with nominal data, we know that we're not going to be doing the one thing that would fall here. There's a z-test of proportion. We're not going to be working with that. Instead, we're going to be dealing with interval data. So we've decided that we are describing one population. We're dealing with interval data. And what comes next is a choice as to what the focus of the question is on. And we have two really easy choices here. The question is either focused on the population mean or the population variance. Now in your textbook, in the flowchart in your textbook, they mention that this is simply your central location. But there's three kinds of central location. There is the mean, the median, and the mode, but you're never going to have a question, a hypothesis test question, about the median or the mode. We're only going to focus on the mean. So that's the only central location or central tendency that you'll have to worry about. So I think it's safe just to put mean is one of the choices and variance is the other choice. And they were very clear in this question in saying that they wanted us to focus on the true mean. So we're not going to focus on variance. So we're not going to be doing a chi-squared test of variance. That's not for this question. So now that we know that we're dealing with describing one population, interval data, focus on the mean, we can now get to our actual formula. It's either going to be a z-test of the mean, or it's going to be a t-test of the mean. And this last choice is decided by what kind of data is given. Either our population standard deviation is given, or the population standard deviation is unknown. Now, there was no mention of a population standard deviation in the question itself, in the setup. If you read through, you won't see them mention population standard deviation anywhere. But you might make the argument, well, I have my data here. I could just calculate the standard deviation. And in fact, we will be calculating the standard deviation from this data. But that doesn't let us say that it's given. Keep in mind that this is not the sample standard deviation, it's the population standard deviation. In order to calculate this, and there are some formulas for population standard deviation, here's one of them. Here's another one. N over N. There's two different formulas. We can calculate it, but these formulas require population data. And we don't have population data. We only have sample data. So we cannot calculate the standard deviation of the population. So we're going to have to say that it's unknown. We're going to have to rule out that it's given, so we're not doing a z-test. It is unknown. Even after we calculate it from the sample data, we're only going to have the sample standard deviation. So we're doing a t-test, and this is found in Chapter 12. So it's the Chapter 12 t-test of one population mean. So that's our job in this question. So next, we're going to have a look at what are the actual steps that we have to cover and what is the actual solution. In order to properly conduct a hypothesis test and get full marks for it, you're going to have to go through a series of steps. And the way that I'm going to label these steps is not necessarily the way that you'll want to label them. I have my own format, and so you certainly don't want to be copying my format. Instead, what I would suggest is in Chapter 12, in this section where they introduce the t-test, have a look at an example there where they're testing, they're doing a t-test of one population mean. Try to follow that as closely as possible. But here I'm going to label my numbers. I'm going to label the steps with a number and a little title. So for example, my very first step is to state the hypotheses. But in order to make this really clear as to what will be worth marks and what won't be worth marks, I'm going to put everything in a green box that you would absolutely have to have with your solution in order to get full marks. So to state my hypotheses, there will be, for any hypothesis test, two hypotheses. These two hypotheses are competing. The first one is called the null hypothesis, and the second is the alternative hypothesis. And one of these is going to represent what it is that we've been asked to determine. We've been asked, is the true mean different or not equals to 142? Now this is going to end up being my alternative hypothesis. How do I know it's the alternative and not the null hypothesis? Well, the basic rule is that the null hypothesis must include the equal sign. If there's a sign being used at all, it has to be the equal sign. Once you get past Chapter 13, you'll find that there will be cases, or there will be questions where you don't use any signs like equals or greater than or less than. But for now, for Chapters 10 to 13, you're always going to be using these signs, equals, not equals, greater than, and less than. And because the sign that we've got here is, this is not equals, we can't put that into the null hypothesis. The null hypothesis must have the equal sign. So this is really all that I need for my first step. I need to state my two hypotheses. However, it is going to be helpful to attach a little bit of a comment to either one of these. For example, they wanted to know, they asked us, is there enough evidence to say that the mean is different from 142? It's a good idea to be able to identify which one of these says yes and which one says no. And you can see that here, this one says yes. This one agrees with what they've been asking us to check out. We would say, if we choose to go with the alternative hypothesis, that's the same as saying yes, the mean does differ from 142. Whereas the null hypothesis would say, no, it doesn't. It does not differ. Now, these comments here, you don't need. You're not going to get any marks for them, so I wouldn't recommend copying these down. You really just need what's in this green box here for full marks. So those are my hypotheses. Now, the second step, you don't even need this entire second step. All that my second step is for is to give me a reminder to check my significance level. A lot of questions use a 5% significance level, so I like to always remind myself to check the significance level just to be sure that they haven't changed it, and in this case they have. They've asked me to use alpha equals to 10%. Now, you won't get any marks for stating this. This is given in the question. So this is just me trying to be organized and not forget to use the right alpha level. The third step, however, you will need the rejection region. You're not going to need the number, you're not going to need the title, but you will need an actual indication as to when you're going to reject the null hypothesis, or maybe when you're going to not reject the null hypothesis. So we're going to have a look at how that works in the rejection region step right here. Now, to make sense of this, I'm going to draw my t-distribution. And the t-distribution at the center has t equals to 0. If it was a z-distribution at the center, it would have z equals to 0, but this is t. The 0 divides my distribution into two parts. I've got my positive side and I've got my negative side. And now what I really need to have here are my rejection regions. Now, if I had equals less than, which I don't, my hypotheses are equals, not equals, but if I did have equals less than, you can think of this as being like an arrow where it points to the lower tail. That would be my rejection region. I would say that if I'm below this point, that's going to be when I reject the null hypothesis. Now, we don't have equals less than, so I'll get rid of this. Instead, if we had equals greater than, then my rejection region would be in this upper tail, and if I was beyond some upper tail, some larger value, then I would reject the null hypothesis. But again, I don't have equals greater than. I've got equals not equals. And for equals not equals, you put a rejection region in both tails. So if I'm lower than this cutoff value here, or if I'm above this cutoff value here, that will be when I'm going to reject the null hypothesis. Same down here. I would reject the null hypothesis if I'm below some value here. This is going to be a negative t value because it's on the lower tail. This will be a positive t value because it's in the upper or the positive side. And both of these values, these t values here, I look these up on the table. I look them up based on two pieces of information. I need to know what half of alpha is, because my 10% gets divided into two tails. So half of alpha over here is half of 10%, that's 5%. The other half that sits over here is also 5%. So I need to know what half of alpha is, and I also need to know my degrees of freedom to be able to look up either one of these. So what are my degrees of freedom? Well, degrees of freedom are calculated as n minus 1, my sample size minus 1. This is equals to 31 minus 1, so it's 30. So this value here that I'm going to be looking up, this is negative t based on 0.05 and 30 degrees of freedom. This one is the exact same, it's just positive. It's dependent upon 0.05 and 30 degrees of freedom. So I need to go to my table, my t-table, and you have a t-table in the back of your book. It looks like this. It's got a little picture with this upper tail shaded in. It lists the degrees of freedom, and then it also gives you t for 0.100, it gives you t for 0.05, it gives you t for 0.025, and so on. We know that we want 0.05. So this is going to be the column that I'm working in. We also know that for the degrees of freedom, we don't want 1 degree of freedom or 2. We want 30 degrees of freedom. So we have to go all the way down to 30, and then we've got our value right here. And if you look this up on your table, you'll find that on the table in your textbook, it comes out to be 1.697. Now this will be different if you look in another textbook, or if you look online, or if you get Excel to do it. You might have more decimal places. But it will round to 1.697. So this is the value I'm going to use, because in your current textbook, this is they go to 3 decimal places for the table value. I know that you're supposed to work things out on this assignment to 4 decimal places, but that's for calculations, not for things that you look up. So what does this mean? Well, it means that this number in the upper tail here is positive 1.697. This number down here is negative 1.697. So in other words, if I'm above positive 1.697, or if I'm below negative 1.697, that's going to be when I reject the null hypothesis. Okay, so how are you going to get this onto your assignment? You can't really draw this. They don't want a handwritten report. And you can't really type this out. Well, we don't need this diagram at all. This was just to make it easy to see what's going on. All that you need for marks is a set of rules as to when you're going to reject. And so I'm going to put those rules right here. I'm just going to say reject the null hypothesis if t is greater than positive 1.697 or t is less than negative 1.697. That's it. That's all you need from this step, is just that statement. You'll find in your textbook, when you're looking at an example for a t-test, they're going to have a statement that looks similar to this. They'll have their own format for writing it. So I would copy that format. Okay, so that's my third step. And just to recap, as far as what's going to be worth marks, this rejection region is necessary. Everything else, talking about the table, won't get you any marks. Showing the diagram won't get you any marks. Actually, you should show them that you've calculated your degrees of freedom. And then way up here, you have to show them your hypotheses. But nothing else will get you any marks. So these parts in the green boxes, these are what you want. Now my fourth step is that I have to do my actual calculation. So I'm going to clear out a little bit of space here. And this will be my next step. This will be my fourth step. This is where I calculate the test statistic. And we've decided, using our flowchart, that it's a t-test of one population mean. And so it's equals to t is sample mean minus the hypothesized mean over the standard deviation of the sample divided by the root of the sample size. A couple of these we have. We know that our sample size is 31. We also know that we've got a hypothesized value of 142. But what we need is our sample mean and our sample standard deviation. And we're going to get those from the sample data. So let's have a look at the sample data. All right, so here's my sample data. And you're allowed to use Excel for this question. So what I'm going to do is I'm just going to type out sample mean and sample standard deviation. And I can make use of Excel formulas. Excel has some built-in formulas that if you want to make use of, that's absolutely fine for this question. This is an Excel question, and it doesn't matter what version of Excel you have. It doesn't matter whether it's a Mac or a PC or even Excel. It could be any spreadsheet program. You're going to be able to make use of this formula. I'm going to start off by typing in equals to let Excel know that I want to use a formula. The formula to find the mean is called average, because the mean and the average are the same thing. And then you have to open up brackets to show it which data you actually want the average for. So now I can highlight my original data. And don't highlight the label, just keep it to the numerical data. Then if you see up here in the formula bar, I have to close my bracket, hit enter, and I've got my mean. The same thing can happen for the sample standard deviation. I'm going to type equals, and the formula is called STDEV, so that's standard deviation. Open a bracket, and make sure that when you're highlighting the data, you don't include the sample mean that we just calculated, because that's not part of the original data. I just want to go from the 141 upwards. Don't include the label at the top. And so once you've highlighted all your data, click into the formula bar, close your bracket, and hit enter. So here are my two values that I needed. And they've asked me to use 4 decimal places, so I'm going to use Excel to chop that down to 4 decimal places. So I've got my mean and my standard deviation. So let's make use of those. My mean was 141.06 or 0968. My standard deviation was 2.0059. So now I can plug those in to my formula. 141.0968 minus my hypothesized mean, which is 142. Standard deviation was 2.0059 over the root of the sample size, that's 31. When you calculate this out, don't forget your square root sign. It comes out to be negative 2.5070. So this is my t statistic, and you absolutely would need to show them this calculation. And you also, well, this, hopefully you can see what our next step is going to be. Here I've worked out what t is equals to, and remember we just worked out when we're going to reject. So my last job is going to be to make a comparison and make a concluding statement. So my conclusion is going to look at the fact that I calculated negative 2.5070, and earlier on we said that we were going to reject the null if we are less than negative 1.697. Well, this number is less than negative 1.697. It's further into the negatives. If you think about t as having 0 here, then this would be negative 1.6 and so on. And then if I want to go all the way to negative 2.57, well, that would put me into my rejection region, because I have to go further into the negatives to get to negative 2.5. So I am in the rejection region. So my conclusion will be to say that I reject the null hypothesis. However, you have to be very careful to not end here. They didn't ask us, and they don't care if we reject the null hypothesis or not. They asked us very clearly this. Let's go up and have a look at the wording. It says, at the 10% significance level, or at alpha equals to 10%, does the sample data provide evidence to show that the true mean temperature of the onion soup differs from 142 degrees? Okay, so let me clear some stuff up here. Our hypotheses looked like this. Our null hypothesis said that the mean is equals to 142. Remember, we put a no next to that. And the alternate was that the mean was not equals to 142, and we put a yes next to that. We then ended up deciding that we're going to reject the null hypothesis. So that means that we're answering with yes. So this is the best way to write out one of these answers. You could say yes, and then go right into the question. At alpha equals to 10%, move the word does. At alpha equals to 10%, the sample data does provide evidence to show that the true mean temperature of the onion soup differs from 142 degrees. It's no longer a question, now it's an answer. So that's it. We just had to move that word and put yes in front, and we've got the perfect answer, because it gives them their words, it answers their question exactly the way that they wanted it answered. So you can't lose any marks here. This is the perfect the perfect way of stating your answer. And even if everybody in the class had the exact same format, that would be fine because it's their format. You're allowed to copy their format. All that we've done is we've really just moved one word. That's it. Even if you just got rid of the word and left it right out, it would still make sense. So that is our answer to part A. It satisfies what they've asked us for here. However, I do need to warn you that for part A, B, C, and D, and every other part of this assignment, anytime you're going to be answering a question that involves sample data, you have to make sure that you check to see if the required conditions are met. So in my next video, I'm going to show you how to do that. You're not going to get full marks unless you run a check of the required conditions. So even though we've answered part A, we won't get full marks for it. We have to run a check of the required conditions. So look for that in my next video.